Game of Thrones horror after the mountain Borson recently broke the deadlift world record with a 501 kilogram lift, which is absolutely completely bonkers. But if he had the lifting power of elite color ant, he'll be able to lift a medium-sized sea dawn completely over his head and carry it home. Not bad. And if the mountain has the same relative strength as the Taria Scrub dung beetle, he could pull a fully loaded Boeing 787 Dreamliner. Compared to us ants and dung beetles and nature's other miniature weightlifters are special because they pull off their amazing feats of strength without bones. And it turns out for every species with an internal skeleton like ours, Earth is a home. Around 20 species without one and maybe more. And that got me thinking, why did we end up with our skeletons on the inside instead of the outside? Hey smart people, Joe here. It's time to face the truth. You're just a meat in a sack tied to a bunch of carefully organized rocks. That's basically what it means to be a vertebrate. We owe everything we are and what we do to our bones. Skeletons are rigid enough for this and flexible enough for this. It's said that we're built in 206 bones, but one of us have extra pair of ribs. Some can even have a pair less. And that doesn't count sphenoids and tendons in our hands, feet, and elsewhere. And speaking of feet, you have 52 bones in your feet alone, twice as many as in your spine. Our hands and feet have more than half the bones in our bodies. Consider that rocks in your fingers moved by muscles and nerves to help you click this video. Oxygen powering the brain that is watching this is fed by blood made in your bones. And you're only even able to hear me talking thanks to these tiny bones in your ears. All of these body parts are about 70% mineral, made of inorganic material called hydroxapatite, which is stiff when compressed, combined with flexible protein called collagen to keep you from shattering. As a result of 20 or so pounds in bones, an average body can withstand 1 ton of compression. And for most of us, they're the last thing we'll leave behind. Bones are pretty awesome. And also awesome. That's the Latin root for bone. Anyway, where did bones come from? That story goes back at least 1.5 billion years ago. Which is a weird place to start because animals didn't even exist yet. But at that moment, violently shifting tectonic plates were washing tons of minerals into ancient oceans. That mineral would one day become skeletons. Life stayed pretty squishy for a while. Early reticular cells depend on water which it lived to support their skeleton-less bodies. But then, around 558 million years ago, through a happy accident of evolution, life split into two and two different skeleton stories began. On one branch, strange creatures began to develop on the first hard protected parts, the precursors of exoskeletons, and this set off an arm race of armor. New shield organisms might have gotten eaten less because they were better protected from the ocean, but partially hard creatures survive more than squishy friends. And like I always say, that's what matters in a game of natural selection. Early exoskeletons got fancier, and we began to see animals with crushing mouthparts, pincers, and full suits of armor. It was during this period we see the earliest arthropods, the group that includes modern insects and crustaceans. On that other branch, and squishy tadpole-like creatures, something else was happening. Soft cartilage-like back rods began to form in order to provide scaffolding for muscles and movement. On the outside, some of these fishy creatures evolved from the cement-like armor. It was the precursor of bone, and soon this hard stuff formed the basis for new structures, like jaws. Very big jaws. Later, this mineral armor was slowly introduced, and those early backbones became mineralized. and together they became the key parts of the vertebrate skeleton as we know it. Over the eons, nature has stumbled on many different ways of desquashifying organisms. The lignin cellulose of plants, calcium-rich cells of mollusks and coral reefs, and mineral bones like ours. But insects and crustaceans built exoskeletons made from chains from modified sugars called gelatin. Gelatin is molecularly similar to cellulose we find in plants, but it's harder and more stable. If you zoom to the lobster shell on a microscopic scale, you see gelatin crystals arranged like stacks of plywood. These special nanostructure arrangements make gelatin exoskeletons incredibly tough for their weight. And that's why insects are so strong pound for pound, or gram for gram. So if exoskeletons are strong, why don't we have them? Like most things in nature, there are trade-offs. For starters, upping an armant's exterior skeleton makes growing more difficult. Every time a lobster or cockroach is ready to size up, they have to molt, shedding their old skeleton that leaves them soft and vulnerable for days or weeks and while they wait for a new outer shell to harden. There's also a weight problem. Strings of ants' legs were at their minimal mass, but scale that ant up to our size, it will be crushed under its own weight. And a few more leg days won't cut it. Because the creature gets bigger, its volume mass increases faster than the cellular strength in hollow exoskeleton legs. On the other hand, or leg, our internal skeletons provide bigger attachments for muscles than exoskeletons would, and our bones grow with our muscles as we get bigger and stronger. But there's also a trade-off here. Bulkier vertebrates have to have more massive bones. Elephant is about 30% bone by weight, not super agile. Shrew is 4% by weight, and while it's quick, it's easy to squish. Humans are about 8.5%, a compromise between strength and mobility, and if we had more bone to be stronger, then we wouldn't move as well. Another problem that is human-sized ant would suffocate. Insects don't really have blood. They have limited circulating systems filled with fluid called hemolymph, mostly full of metabolic stuff and immune cells. Insects breathe through tiny holes in their exoskeletons that deliver oxygen to their tubes. This distant oxygen can travel down the tubes depending on its concentration in the air. During the prehistoric time, two-footed dragonflies did exist because the atmosphere's oxygen levels were higher. Plus, having all your muscles attached to your outside means that while you're strong, you're not that flexible. Yeah, let's see you do this, super strong grasshopper. So, chitin exoskeleton, super strong, but only if you're small. Human-sized ant, they're lethargic, very crumpled, can't do yoga. Remember that split we talked about earlier? One branch leads to bugs and exoskeletons, and the other branch eventually leads to you and me and every other vertebrate. And what's crazy to think about it is that we're all this way because of luck or chance. Because when our ancestors began to build hard bodies, the only ingredients they had to choose were nature provided. Those shifting tectonic plates a billion and a half of years ago welded and slapped the rocks and made the earth crust rub together. All the minerals they are made of wash into the sea. And one of those minerals, calcium carbonate, happens to be a very useful building material. Evolution got the chef stuck in the home during COVID quarantine, by which I mean you gotta use whatever ingredients you have got around. Our very distant relatives were bathed in calcium from those grinding tectonic plates, and so they used this to build the earliest bone-like tissues. The evolutionary bone wasn't a grand aha moment in the story of evolution. It's just one of such many chance events influenced by the environment that sent one arm of life on the earth to a completely new course. And vertebrates aren't the only ones who ended up building bodies out of calcium. Invertebrates, mollusks to coral to starfish, all use calcium to build their body support structures. Exoskeleton having animals like insects and other arthropods just went another way, building children's exoskeletons thanks to the chance events of evolution. And if we played the story from back again to the beginning, perhaps our land would be built differently too. Which means, as we know now, we'd be very small. But at least we'd have an armor, and maybe some sweet pincers, and even some horns. And then, what would ants look like? Stay curious.